Good morning, and thanks for coming. Am I loud enough for everybody in the back to hear me okay? All right, good. So the topic of my talk today is, do statistical models understand the world? And the word understand is a little bit vague, but I'll try to give you a better idea of what I mean by that as we move through the talk. The work that I'm presenting today is based on a few papers that I'll give you some pointers to at the end of the talk. And most of what I'm saying in the slides today was joint work with two of my colleagues, John and Christian. The basic idea for why we're worrying about this problem is that deep neural networks have started to perform at human-level accuracy on a variety of test sets. So when I say test set, what I mean is that we show the network the same kinds of inputs that it was trained on, and we ask it to process those inputs in the same way that we trained it to process the training set inputs. When we evaluate the network in this way, it performs as well or nearly as well as humans on a wide variety of tasks. It's been used for object recognition, where it needs to recognize thousands of different categories of objects. You could argue that some of why the network is able to match human performance is that humans don't really know the difference between very similar kinds of objects like Siberian huskies and Alaskan huskies. But overall, the network is still performing very well, and it's able to match the same quantitative number that humans get, even if part of why it's able to do that is just that the task is not especially well suited to human abilities. Neural networks are also very good at recognizing faces. Facebook's deep face system gets about the same accuracy on recognizing faces as humans do. Once again, this is when we're considering a task where the computer is on relatively equal footing to the human. It's evaluating faces that are of people that the human does not know. If we compared your ability to recognize your friends and family members to a computer's ability to recognize them, you would still probably win. But when we test you against a computer recognizing people who are strangers to you, then the computer does about as well as you do. I personally, along with some of my colleagues at Google, trained a neural network to read address numbers from photos in Street View. And this same network can also break the reCAPTCHA system by transcribing obfuscated text. Machine learning is actually better than humans at reading CAPTCHAs now, which is why Google has adjusted the way that we use CAPTCHAs. But the basic idea is that in a lot of ways, when we test machine learning systems in exactly the same way that they are trained, they match human-level performance on very sophisticated tasks. This naturally raises the question, does this mean that we have achieved real AI and that the machine understands these tasks where it is able to match human-level performance? And if I were not, since I'm doing the talk today, the answer is pretty obviously going to be no. But I'm going to try to give you some specific ways of being able to tell that we don't understand the task. Defining the word understand is actually a very difficult philosophical question, and I'm not going to weigh in on the philosophy. But I'll give you one example of some things that philosophers have said about this problem, and then I'm going to do kind of an engineer's take on the philosophical thought experiment. So John Searle is a philosopher of mind at Berkeley, and he proposed a thought experiment that's known as the Chinese room thought experiment. So John Searle himself does not speak Chinese at all. And he said, in this thought experiment, suppose that you lock him in a room with an instruction manual that tells you how to respond to every conceivable Chinese sentence. And then people pass cards with Chinese written on them into the room where he is sitting. So he gets a card that looks like this, and he looks up that card in his instruction manual, and then he passes back out a card that has the correct Chinese response written on it. So that response might look something like this. So John Searle argued that even though he is able to perform the task, he does not really understand the task. Now, there's a lot of philosophical debate about how to interpret this. Some people argue that the combination of the instruction manual and John Searle himself understand Chinese as a system. I'm not going to weigh into those particular interpretations. But as an engineer, my take on this thought experiment is that you could test whether the system understands Chinese by providing John Searle with an incomplete instruction book and then asking him a question about an input that does not appear in his instruction book. We turned out to run this experiment for neural networks inadvertently about 5 years ago. My colleague Christian, who's one of the main people studying computer vision with neural networks at Google, was studying neural networks used for object recognition, and he was interested in understanding what features these neural networks use to identify different object classes. So he decided he would load an image of one kind of object, and then he would use gradient ascent. He would ask the network how it could gradually change an image to make it appear to belong to another class. So on this page, I'm taking images of objects, and I'm telling the network to gradually turn them into airplanes. When Christian ran this experiment, he thought that it would show some kind of recognizable feature that we could tell the network is using to identify these objects. For example, it maybe when we turn things into airplanes, it would put wings on them. As you can see, there isn't much going on that we can actually identify. This here is the original image of a ship, and we gradually morph it into something that still looks like a ship. But at this point, the network now says that it's an airplane. The same thing happens for this car and for this cat. You can see the cat's face kind of turns gray, and maybe his nose looks a bit like the fuselage of an airplane. But most of these things, you can't even really tell what's changing or why the network might think that there's an airplane there. And to be honest, the first time you code this up, it's a little bit spooky, and my natural reaction was to think I had a bug. But if you go and you examine the images, there actually is small differences between them, and you can print out the probability that the network prints for each class, and it does reliably go up. And several people have replicated this. So at this point, we're convinced that this effect is real. So having accidentally discovered this, we realized that we've essentially found a way of testing whether the neural network actually understands the task that it's studying. We've asked it to do something that's not in its instruction book. You can think of the data that we trained the network on as being the Chinese room instruction book for a machine learning classifier. Specifically, this instruction book says, when you get an object that looks like this, say it's an airplane. When you get an object that looks like this specific object, say it's a cat, and so on for 50,000 specific cases. You can also think of some of the statistical processes like maximum likelihood estimation as expanding the instruction book by saying, try to think what probability distribution generated all of these examples, and then when you see new ones, label them according to the same probability distribution. But essentially, the data is the instruction book that the machine learning model is trying to use to do the task that we're asking it to perform. And when we then ask it to step in directions that are not constrained to look like the data, it can turn out to visit places that are very statistically different from the data. And when it goes there, it no longer has the correct answer. So at first, we thought this might just be a problem with neural networks. And quickly, we decided to test whether other machine learning models have the same problem. It turns out that essentially all machine learning models have this problem to some extent. This is a shallow softmax regression classifier. So it's based on just one matrix multiplication to perform classification. What we did here is we started by loading an image of a 9, and we asked it to turn that 9 into a 0. So it believes this is a 0. Each yellow box indicates when we've hit another class. So then we said, OK, well, keep on morphing it. Turn it into a 1, a 2, a 3, a 4, a 5, a 6, a 7, an 8. And well, it actually made something that looks like a 9, but it started with a 9, so that's not very impressive. So it turns out that even very simple machine learning models, not just the sophisticated deep ones, have this problem. So what's going on here? Have all of my machine learning colleagues and I been ripping you off by tricking you into thinking that our methods work well? Well, no, not really. It's more that the way we've been evaluating models and the way that models have been learning has been an incomplete picture. And so we didn't understand what our models were learning, and our models didn't understand what we were asking them to learn. There's a researcher named Bob Sturm that has a very good analogy for describing this situation. There was a horse here in Germany in about 1905 called Clever Hans, and he was owned by a PE teacher who taught him to do arithmetic. You could look at the horse and say, what's 3 plus 2? And then he would tap his hoof on the ground 5 times. And huge crowds would gather around him and watch in amazement, and he would tap his hoof again and again and again. And when he tapped the 5th time, everybody would respond to the, ooh, he knows how to add. And then the horse would stop tapping. So you can see what the problem is here. He traveled Europe for a long time. His owner was completely honest. His owner was not trying to make money off of this. He never charged admission to see the horse. And presumably the horse wasn't intending to mess with anybody. He was just doing what he was trained to do. But the psychologist came and studied him and found that under laboratory conditions, the horse could not perform arithmetic. If a single person asked him to do arithmetic while wearing a mask over his face and was careful not to exhibit any signs of emotion, the horse had no idea when to stop tapping. So essentially, the horse had learned to perform the task of arithmetic according to our evaluation metric of impressing a large crowd of people. Similarly, machine learning algorithms have learned how to perform the task of recognizing objects or recognizing speech under the criterion of performing well on data that is statistically similar to the training data. But that means when we provide the model with other inputs, it may not necessarily do the right thing, just as Clever Hans doesn't do the right thing if you're wearing a mask when you ask him to do arithmetic. So why exactly are machine learning algorithms doing the wrong thing? When we first published our results in 2013, most people's gut instinct, including ours, was that this was a form of some kind of overfitting, and that it resulted from the functions that deep networks learn being highly complex. So in this view, we have a training set consisting of these 3 X's, and we want to put sort of a dark bluish-green blob surrounding everywhere we believe that there are X's. This dark greenish blob represents what the model believes is the space of X examples. Our other category of examples is these O's, and we want the bright green blobs to surround everywhere that we think that there are O's. So in this cartoon picture, our model is so nonlinear and multimodal and highly complicated that it just overfits the data really badly. It happens to shoot a wiggly blob of probability mass around the training set X's and another one around the training set O's. But it's also decided that there are O's over here, as you can tell by the light green, and it believes that there are O's over here, as you can tell by the blue. But a human would probably not make that same decision. It's decided there are X's over here, as you can tell by the blue. A human would decide that this is an O, so we've colored it as red to show that the machine learning algorithm has misclassified it. A human would say this point is very close to this O, therefore it's probably an O. And likewise, a human would say this point is very close to these X's, therefore it's probably an X. But the machine learning algorithm, just by chance, has decided to label them differently. So that's what everybody thought was happening. What I'm going to argue in this talk is that something very different is happening. I'm going to argue that you can actually get adversarial examples as a result of something that is more similar to underfitting than overfitting. It seems paradoxical because adversarial examples are a failure to generalize. What I'm going to say is that adversarial examples occur because we use far too simple of a decision function class. So here's the same training set again, split in half by a linear model. Now we have an adversarial example over here. It's extremely close to these training set O's, and it looks like an extension of this curved manifold of O's, but it lies on the X side of this linear dividing hyperplane. Similarly, this point here is extremely close to these X's, and it's in the middle of this big C shape. It's far from the ends of the C shape, so it looks like it's not on that manifold of O's. But because it's on this side of the linear separating hyperplane, we've classified it as being an O, which is why I've drawn it in red to show that the learning algorithm failed to recognize that it was an X. So linear classifiers can often oversimplify a problem, and if you just search for things on one side of the boundary or the other, you can get adversarial examples that way. One reason that people automatically thought that adversarial examples were a result of overfitting is that people have some kind of misleading intuitions about what model capacity means. Usually in machine learning, we say that models either have low capacity, which means that they can't represent many different functions, or they have high capacity, which means they can represent almost anything you want and they can learn lots of different functions. Usually, if you have low capacity, you're prone to underfitting, and if you have high capacity, you're prone to overfitting. A lot of people have this incorrect intuition that a low capacity model can't be highly confident in multiple different locations. That's not actually correct. It's a little bit more subtle. A low capacity model does not have much control over where it places its confidence. It's forced to distribute its confidence in some sort of predefined pattern. So here I'm comparing two different kinds of models that both have low capacity. One is a linear model, where it says that the probability of one class is, that the log of that probability is proportional to a linear function, which I've drawn in red here. And the other model is an RBF network, which says that the probability of each class occurs as a little bump in space. So the linear model has the task of saying that the probability of being an X is high near these training set X's, and the probability of being an O is high near these training set O's. In order to do that, it needs to make the log probability of being an O be low over here and high over here. Because this function is a line, that means it's forced to be even lower over here, far to the left, and even higher here to the right. So linear models actually gain confidence when they're forced to extrapolate. If we show it some kind of data point it's never seen before far off to the right, it says, that definitely is an O. It's even more likely to be an O than the O's that I have specifically seen in the training set. To a human observer, this seems a little bit irrational. When we step outside the area that we're familiar with, we usually become less confident. When we're confronted with something unfamiliar, we might make our best guess about what to do, but we tend to be less confident that that guess is correct. And here, the linear model becomes more and more confident the more unfamiliar it is with the situation. RBF models do not have this problem. RBF models have other problems. They have difficulty extrapolating at all, but when they extrapolate, they become less confident. And both of these are examples of models with low capacity. So what I'm arguing is that adversarial examples could come from this phenomenon of extrapolating with greater and greater confidence, which is still a form of low model capacity. Yeah?
Why do we call RBF low capacity model?
I'm saying it's an RBF model that places a single bump for each class. It's not a deep RBF network.
RBF have infinite dimensions?
No. Well, okay, so VC dimension, you're allowed to choose the points. But if the points are arranged arbitrarily, then you can't necessarily shatter them. So a neural network could learn to shatter points that you have chosen their position. But an RBF network with one Gaussian bump per class requires that the points be arranged in a way that they correspond to the bumps.
One Gaussian per class.
Yeah, so here I'm talking about just one Gaussian per class, yeah. And for the linear model, I'm talking about just one linear discriminant. So deep networks are very piecewise linear, or rather we build them out of piecewise linear pieces. The rectified linear unit is probably the most popular activation function right now, and it consists of one horizontal piece and then one piece that is linear with learnable slope and direction. There's another model called maxout that I personally have used for a lot of things. It's also defined to be piecewise linear, and you can learn the slope of each of the pieces, but it's still piecewise linear. We also use sigmoid networks frequently for neural nets, or at least we did until a few years ago. Now they're less popular. But for sigmoids to work well, we usually need to very carefully tune them, especially at initialization time, to make sure that they operate primarily in the linear regime of the sigmoid. So even sigmoid networks actually behave very linearly. The LSTM network that people use for modeling long sequences over time is also based on this principle of linearity. Specifically, the way we transfer information from one time step to the next is we just add the state from a previous time step to the current one. So addition is a simple case of a linear operation. Basically, all of these deep neural nets are based on trying to be as linear as possible. This suggests that if we just model the network as a linear function, we might be able to generate adversarial examples to it. So we designed a simple one-step procedure for finding an adversarial example. You no longer need to use gradient descent to search for it. You can find it in a single step. It's a probabilistic outcome. It's not guaranteed to be an adversarial example. But in practice, we find that this method succeeds on over 99% of inputs. The basic idea is that we can approximate the neural network with a single linear function of its input. And then we can say that we assume each pixel has some minimum level of precision, and that if you change the pixel by less than that amount, it would be irrational to believe that the class could change. So for example, if you're storing your images with 8 bits per pixel, then that means the smallest change you can discriminate in your bit storage pattern is 1 over 255, if the pixels have a range from 0 to 1. So if we say that we're going to change each pixel by 1 over 255 or less, and we model our network as being linear, it means all we need to do is take the sign of the gradient of the network and then add or subtract epsilon times that sign, where we choose epsilon to be something that we think should not affect the classification of the image. So here we've got a panda from the Imagenet data set. It's originally classified by a state-of-the-art Imagenet processing network as being a panda with 57.7% confidence. Then we take the gradient of the neural network's cost function. We say, what direction in input space will make you become wrong the fastest? And we take the sign of the gradient, which helps us solve for the most damaging change we can make to every pixel separately. And then we add epsilon times that modified gradient. The gradient itself here corresponds to the nematode class with low confidence. The gradient on its own doesn't mean much of anything. But when you combine the two, we end up with an image that to us looks like a panda, but the network has classified as being a gibbon with 99.3% confidence. So it's actually even more confident that this is a gibbon than it was that this is a panda. So here we made an assumption that maybe the network is very linear and that you could design an algorithm to confuse it under this assumption of linearity. And then we went ahead and we successfully confused it. That doesn't necessarily guarantee that linearity is the full explanation for why it's confusable. So we ran a few other experiments to try to get a better idea of whether linearity is the underlying problem or not. To give you a brief view of how this linear problem actually works on a simpler model than Imagenet, let me show you what things look like with logistic regression. So logistic regression, we've got two different classes. Here it's 7s and 3s, and we're learning one set of weights. So this image that we basically just multiply with the other image. We take each pixel in here and multiply it by the corresponding pixel in here, and we add up all the results. And then if the resulting number is positive, we think it's one class. If the resulting number is negative, we think it's the other class. I actually forget whether 7s are positive or negative, and it can be a little bit hard to tell from this weight. The most damaging change you can make under the constraint that no pixel can change by some amount epsilon is to add or subtract the sign of these weights. These are the images that we end up getting when we do this kind of addition. Here I've chosen a fairly large value of epsilon so that you can see what we added. On the previous slide, I chose a small version of epsilon to demonstrate that the model is very easy to confuse. So in this slide, you can see that even when the adversarial perturbation is pretty big, we just ignore it. To us, the most salient thing is the foreground object, that there's a 7 here. What the neural network sees, or actually in this case, what the logistic regression model sees, is the world's most perfectly quintessential example of a 3. Its weights are designed to look for 3s by looking for this pattern, and we have fed it something that maximally matches that pattern at every single pixel. So it's almost like steganography, the practice of sending secret messages by hiding them in another signal. It's possible to send a secret message to somebody by encoding one image in only the smallest bits of another image. And then when people look at it, they see the larger 7 bits, and they don't realize that you've hidden something in the small bit unless they know specifically to look for it. Here, we're essentially hiding a message in the smallest bits of an image, and then the neural net is forced to actually read the secret message rather than the primary one. The principle here is all about aligning with what the system responds to. And so because we know how the system responds to descriptions of 3s, we send it a steganographic message with such a perfectly recognizable 3 that the steganographic message is more coherent than the primary message. An important part of this story is that the space is high dimensional. So here there are 784 pixels. And every pixel is getting to vote for the wrong class with a small perturbation of size epsilon. So a perturbation of size epsilon on its own is not very powerful. But when you have 784 times epsilon, then even if epsilon is on the order of 1 over 100, you can end up with an overall perturbation of the class response function that's greater than 1. So because you have both a high-dimensional space and because linear functions combine evidence from different features by simply adding them together, you can take a very large number of tiny pieces of evidence and have the model conclude that you have a preponderance of evidence for one specific class, even if all of the evidence in favor of that class was on its own barely noticeable. This same principle actually applies on Imagenet. After we published our paper, Andrei Karpathy, one of the organizers of the Imagenet large-scale visual recognition challenge, published a blog post where he took different Imagenet categories and learned linear models for them, which is actually, the linear model is not going to perform very well because Imagenet data is so complicated. But you can take this image of a goldfish, add the weights for the daisy class, and end up with the model being more confident that this is a daisy than it was that this was a goldfish. So this principle seems to generalize fairly well to different data sets, and it works on very simple traditional linear models. It's not specific to deep learning. So to convince you that deep learning models actually behave linearly and that that's part of their problem, we decided to trace out linear paths in input space and plot the response of the model. So here I have a picture of a car, and as we scan backwards, going right to left, bottom to top, we're subtracting this image off of that car. And then as we move left to right, top to bottom, we're adding that image back on. So this is all just tracing out a linear path in input space. To make it so you can see each image, I've then rescaled the brightness of the image so that they all have the same total range of pixel values. But the input to the network itself is tracing out a linear path in high-dimensional space. The x-axis of this plot shows the magnitude of the image that we have subtracted or added to the network's input. When we're at 0, that means that we're actually getting the original picture of the car. On the y-axis, I'm plotting what are called the logits. They're the arguments to the softmax that the model produces. So when you take e to the x of these values and then renormalize them to get a probability distribution, they'll give you a probability distribution over classes. If I showed you the probability distribution over classes, it would look very flat because they saturate to 1 pretty much everywhere right away. But by looking at the logits, you can see that the logits themselves are pretty much split into 2 linear pieces, where each logit will rise for a long time and then fall for a long time, or vice versa. But except for in the vicinity of the data set, we're getting this overconfident linear extrapolation behavior. that I was arguing earlier is irrational. What this means is that there's a very thin manifold, the area immediately surrounding the data, where the model behaves accurately. And everywhere else, the model is just clever Hans tapping his foot and waiting for a single signal to stop. You can visit random points in Rn, and they will generally turn out to be some kind of hallucination. In this slide, we went one step further. What we did was we added one step of the sign of the gradient to try to turn things into airplanes. So we're just drawing random values from a Gaussian. Everything that has a pink box around it is something that the model thought was an object rather than nothing. It had a confidence greater than 50% that one of the 10 classes it was trained on is present. So it's not very surprising that it would think that most of Rn belongs to some class or another. Squares that are also boxed in yellow are squares where we managed to convince it that this was an airplane. So you can see that about a quarter of our samples, we convinced the model was an airplane. Airplanes are the hardest class. Other classes, like ironically enough, horses, are very common. So the clever Hans metaphor is appropriate because this model actually believes that about 70% of Rn is a horse with high confidence. You can see there's just a few places where there's not a box of either color. So here there's this black box. Here there's this black box. Those are the only cases out of these, I believe it's 100 samples, where the model not only knew it wasn't a horse, but also knew that it was not any object at all. So it does occasionally get the right answer, but it's a very, very rare result. Hallucinations occur almost everywhere, and you don't really need to look for them at all. It's harder to find an off data set point that's treated well than to find an off data set point that's treated correctly. Okay, so a lot of people hear about this problem and immediately think that it's going to be easy to fix with some kind of off-the-shelf machine learning technique that we've used to regularize models for years. So a lot of people say, well, you're just looking at a single network. And of course, a single network is going to have a bad hypothesis. What if you take several networks and have them vote on the input? Well, we tested that, and it turns out not to really help at all. You can generate adversarial examples to the whole ensemble, and the ensemble will misclassify it. More disappointingly, you can generate adversarial examples to a single member of the ensemble, and the rest of the ensemble will misclassify those too. Somebody made a comment on the internet somewhere after there was an article about these results, where somebody speculated that maybe the human visual system solves this problem by rapidly glancing many different places, and that maybe one individual glance could give you an adversarial example, but the next glance will be shifted slightly and you'll classify that one correctly. Well, that view is based on the assumption that adversarial examples are rare, and I just showed you that they occur almost everywhere. Anyway, we tested this. You can actually have a model glimpse 20 different positions in the same image and then vote, and it's still vulnerable to adversarial examples, even if you generate the adversarial example with respect to only one glimpse. Another thing is just weight decay. You regularize the model's parameters to be small. It's a typical way of preventing overfitting. We experimented with weight decay extensively in our first paper introducing the idea of adversarial examples and never got it to resist them, even in simple linear models like softmax regression. And then in our more recent paper, after we figured out this idea that the sign of the gradient is a good thing to use to regularize, we switched to using L1 weight decay, and it still doesn't work. You can also try to prevent adversarial examples by regularizing the Jacobian to be very flat. That doesn't seem to work either. It will tell you to resist adversarial perturbation in an infinitesimally small neighborhood, but if you make the perturbations larger than infinitesimal, you'll still get them wrong. A lot of people have also thought that you could train the network to resist adversarial examples just by adding a lot of noise to its input. Or that when you classify, you could add noise to the input in the hopes that the noise will cancel out the adversarial perturbation. Neither of those really works. It turns out that the direction is very important for the adversarial perturbation, and isotropic noise is very unlikely to hit the correct direction to either cause or fix the adversarial example, unless you make the noise so big that it essentially erases the input. A lot of people believe that generative modeling will automatically fix this problem, that if you just use unsupervised pre-training to regularize your model, that it will learn that adversarial examples are statistically unusual, that there's a low p of x where they occur, and therefore that you'll classify them correctly somehow. I think that approach could be used to identify when you've encountered an adversarial example and then refuse to classify it. But I'm not sure that this approach can do anything to make us classify the example correctly. So when I show you an image of a car that has been perturbed to make the model think it's an airplane, it would be better than nothing if the model could say, I'm aware that this image is doctored and I refuse to proceed any further. But that's still kind of unsatisfying because we as human beings can say, well, that image is clearly a car. Generative modeling would allow you to do the former, but there's not an obvious path to how it would allow you to do the latter. If you know that p of x is low, then you know that p of y comma x needs to be low for all values of y, but you don't know which value of y should have the highest p of y comma x. Another strategy that I thought was really cool is some people from Panasonic Research had the idea of training a denoising autoencoder where the noise distribution is the adversarial example distribution. So you essentially train a denoising autoencoder to take an adversarial example and map it to a clean example. And this turned out not to work, which is too bad because I thought it was a very elegant solution. I think the reason that it doesn't work is that the autoencoder adds 2 more layers to your network, and the autoencoder is still based on linear layers. So you've basically just multiplied 2 more matrices into your Jacobian. The other thing is I showed you how RBF networks are not especially vulnerable to adversarial examples. So I thought that maybe by training a deep RBF network, I could overcome this problem. And I'm not saying it's impossible for a deep RBF network to work, but I have not been able to get deep RBF networks to perform nearly as well as linear neural networks on the clean task. It's true that they resist adversarial examples, but at the cost of performing much worse on the original task that we care about. But possibly somebody else could think of a better way of training RBF networks. So why are we using these linear models? Are they the only thing that's available? RBF networks are actually able to behave reasonably far from the data. Here we say, here's a 9, please turn it into a 0. The RBF network turns it into a fairly convincing 0 right around here. And then we start turning it into a 1, a 2, a 3, a 4, a 5, a 6, a 7, an 8, a 9, and so on. They're not the world's most accurate and high fidelity numbers, but you can tell that it has the idea of what numbers look like, and it successfully traversed a lot of Rn right there. So why don't we just use RBFs everywhere? Well, the simple answer is that anything that is easy to optimize is easy to perturb, and vice versa. If a model is hard to perturb, it's hard to optimize. So in a deep network, we need to have gradient flow from the output to the input. So I've tried to highlight this path of information flow from the label to the input. When we train the model, we want to update all of the model's parameters, including this one right here, this weight. If we want to modify this weight, we need there to be a strong path of information flow from here to here. But if this weight is not 0, then it will also imply that there's a large derivative with respect to this pixel here. If this pixel has a large derivative, it means that modifying this pixel modifies this output significantly. So for anything where the backpropagation algorithm works, it looks like it's also going to be easy to perturb. This suggests that if we really want to overcome adversarial examples, we might need to come up with a different way of optimizing that's more able to deal with small gradients than any of the technologies for optimization we currently have. And so it's possible that something like an RBF network, which right now we're not able to get to achieve good performance on the training set, could become a more interesting model in the future if we get more powerful optimization methods that's able to explore the flat regions of the RBF objective function space more efficiently. In the meantime, what we can do instead is we can try to improve the neural nets we've got by training them to represent the right function. So I told you earlier that the linear function is kind of irrational, And the RBF function that falls away as you move away from the data is somewhat more reasonable from a human intuitive point of view of wanting to respond with low confidence to things that you're not familiar with. Well, it turns out that a neural network can represent any function to an arbitrary degree of accuracy, so long as you make it big enough. That suggests that while a linear model like a support vector machine doesn't have the chance to overcome adversarial examples, a neural network does have that chance if we just train it to correctly. The universal approximator theorem doesn't guarantee that the learning process will be able to find that function, but we do know it's at least representable. So the way we can try to find this function is we can actually train the network on adversarial examples. During training, we can continuously generate these examples and tell the network to classify them the same as the original clean example. So it's essentially, we've added a prior to the optimization process where we say that the objective function should be very flat within a max norm ball surrounding each of the training set points. When we do this, we actually got a new state-of-the-art result on MNIST, which has since been beaten by Harry Valpola. But at the time we ran this experiment, we got an average of 78.2, or 0.0782%. So it's MNIST. The numbers are getting ridiculously small. The important thing is that when we use adversarial training, we reach lower error on the clean test set than when we do not use adversarial training. So even though we're training on adversarial examples that we don't expect the model to ever see, learning to fit those examples forces it to come up with a more correct explanation. It forces clever Hans to really learn to do arithmetic rather than to just read people's faces. And so when we've got something that's more like the real deal, it's actually able to do better at the original task than the original model was. If we also look at the performance on adversarial examples over time during training, we can see that standard training without adversarial examples never really changes your ability to classify adversarial examples at all. You always get all of them wrong. But if we train on adversarial examples, then over time we start to get more and more of them right. And as of this speech, the best model that I've got is down to about 3% error on adversarial MNIST, which is better than, it's significantly better than RBF networks. RBF networks get about 50% error on adversarial MNIST if you just train them naturally. So neural nets with this adversarial training are able to become more resistant to adversarial examples than other machine learning models are when they're just trained naturally. There are still some weaknesses. So here we have an adversarial trained network, and we're asking it to morph this truck into all of the other 10 classes that it saw in the data set. And you can see that most of the images just look like garbage, or maybe they still look like the truck. There's only one case where it really succeeded. This right here is the bird class, and it's kind of made the front of the truck melt and become the chest of the bird, and it's drawn a very faint beak out of the mirror on the left side of the truck. And it's turned the rack of the truck into some nice little plumage, and it's turned this reflection on the windshield into an eye. So yeah, this is neural network art here, where it has figured out how to do sort of an impressionist truck bird hybrid. Most of the time, you do not get interesting art. Here, we ask it to morph a cat into all the different classes, and we get something that looks just like a mess of sound and fury signifying nothing. So one thing that's kind of horrifying about adversarial examples is that they actually generalize across different data sets and different models. If you have two different data sets for the same task, so here we've got a collection of 3s and 7s, and then over here we've got different 3s and 7s, and we train different models on them, you're going to learn more or less the same discriminating function in both cases. And that means that both models are going to be vulnerable to the same adversarial examples. So that means that this actually has implications for computer security. If you want to use machine learning in a context where somebody has an incentive to fool your model, like if you're using machine learning to filter out spam, then you've got to be aware of these adversarial examples. People do not need access to your model to figure out how to fool it. They can train their own model on a data set that they gathered themselves, and as long as that data set corresponds to the same task, they can train their own model, generate adversarial examples for their model, and then feed those into your system. So they can take images that are clearly advertising, perturb them slightly to look like they're not advertising, and then upload them to your platform that you want to keep spam out of. And if you do not have the right measures in place to deal with adversarial examples, your model will go ahead and classify those as being clean with high probability. People also often ask me if there are adversarial examples in the human brain. And we can tell that the adversarial examples that affect our machine learning models do not affect our brain because of that cross-model transfer that I just described. Adversarial examples move from one modern machine learning algorithm to another, but they don't seem to affect us. That doesn't mean that we have no adversarial examples, though. It just means that we have different ones than the machine learning models do. So this is an example of something that confuses our visual system. These circles are actually concentric. They are not spirals intertwined with each other. But the arrangement of edges fools our visual system into thinking that it's a spiral that intertwines with itself. There are other forms of adversarial examples that affect human beings. For example, if you flash strobe lights at the same frequency as the human cortical processing, you can cause a seizure even in healthy people. It's essentially the same thing as, it's similar to epilepsy, but induced by something that you actually observed. It's similar to what you could do with the weights of the neural network, where you find the properties that the system is responsive to, and then you just provide a stimulus with that exact property, and you get a disproportionate response. So the goal of studying adversarial examples is not necessarily to get rid of all of them forever, but to understand what they are, and to make sure that we know how to use them and to make them as rare as possible. In conclusion, I'd like to clean up just a few common misconceptions, which hopefully you got this from the talk, but I'll just summarize quickly. A lot of people think that adversarial examples are rare or that they occur in small pockets, but they're actually ubiquitous. They're almost everywhere in RN, and essentially they occur in half spaces rather than small pockets. Deep learning is not the only kind of machine learning that's vulnerable to adversarial examples. Essentially every form of machine learning I've tested is vulnerable. Deep learning actually is very well posed to overcome adversarial examples because of the universal approximator theorem. A lot of people also think that they're safe from adversarial examples because their potential attacker might not have access to their model. But it's important to understand that you can actually attack a model without access to the model itself or even to its training set. A lot of people also think that adversarial examples are very easy to fix with standard regularization techniques. But so far, no technique we've tested actually works. So in conclusion, many modern machine learning algorithms get the right answer for the wrong reason, just like clever Hans. And when you apply them to unnatural inputs, they almost always get the wrong answer. Adversarial training can expand the region where these models get the right answer, but there's still a long way to go. And right now, deep learning seems like it's on a good course to go ahead and figure out some way of expanding our instruction book by making new adversarial training algorithms that force the model to be right at every point in RN, not just on the training data. Thanks, and I'm available for questions.
Excellent talk. Thank you very much. Very
Thank you.
Phenomena that you described. In the initial part, set out with a different interpretation that I would have put under those described phenomena. And then during the course of your talk, I found out that your interpretation is just there's a duality to my interpretation. And this is very abstract, so I'll try to convey this. You started out with a hypothesis that in particular linear models fail, and that's somehow connected to this linearity thing. And then you applied methods to test the hypothesis. And the method was adding noise. And in some circumstances, you can just swap the two sides. And in my model, the problem caused is the peculiar nature of the noise, and your attribution to linearity is just the sharpest tool to test this noise thing. If you ask me to change the impression of the people here so that I could confuse someone sitting here with my mother, I would just dim out the light. And then probability rises that you swap the two sides. And I think constraints in the image input that are produced by the continuity constraints of our physical world do not apply to changing your bits in your data. So you can just, the images that you present from a natural world have continuity constraints. And if your bit pattern destroys these constraints, you deduce the learning network on a path where it gets just insecure.
Right, so I'm supposed to repeat the questions for the camera. And this is kind of a long statement. I'll repeat one thing for the camera, which is you said that natural images have continuity constraints and that we aren't actually imposing those continuity constraints at all in this model. So one thing we've tried to do is actually using local contrast normalization to sort of blur and smooth out the adversarial perturbation before the model is allowed to see it. And it seems like as long as the perturbation is more or less aligned with the gradient, that it can still be very harmful even if it is more spatially continuous. Yeah.
Okay.
Yeah. I think I'm more or less out of time. Or...
We have a few minutes left.
Okay.
Maybe one question. You said that the gradient descent methods are the cause, the root cause of the problems in some way. So do you think that kind of autonomous learning algorithms that don't depend on such a signal coming down are more robust or could be more robust?
So Nico asked if learning algorithms other than gradient descent that don't have a signal coming down could be more robust. I think the issue is not so much that there's a signal coming down as that SGD needs to be able to make very small moves. So SGD works by saying, if I make a very tiny move, am I going to get a very tiny increase or a very tiny decrease in my cost function? And I don't think it matters whether you decide that using a top-down or a bottom-up signal. The important thing is that tiny changes are meant to reliably make tiny changes that add up to big changes. Instead, I think we need an optimization algorithm that can make very large jumps on a surface where tiny changes don't cause much of a discernible change at all. As long as tiny changes cause a discernible change, then you can make tiny changes to create an adversarial example.
Okay, then. Thank you very much. Ian again.
Thanks.